When a current-carrying loop is placed in a uniform magnetic field, it experiences a torque that causes it to rotate. We will analyze this using a rectangular loop of area A placed within a field B. Let's define the current I flowing clockwise through the loop. We will examine the forces acting on each of the 4 segments, labeled L1 through L4, to understand the resulting motion. On the sides parallel to the magnetic field, the angle between the current and the field is 0 or 180 degrees. Therefore, the magnetic force on these segments is 0, and they contribute nothing to the torque. Now look at the vertical sides of length L. Since they are perpendicular to the field, they experience maximum force. Using the right-hand rule, we see force F1 pulls out toward us, while F3 pushes away. To calculate torque, we look at the loop from above. We define a normal vector, n, which is perpendicular to the plane of the loop. The angle theta is the angle between this normal vector and the magnetic field B. Torque is force times the perpendicular distance from the axis of rotation. With the loop width labeled W, the distance from the center to the force line is determined by the sine of the angle theta. By multiplying the force on the vertical sides by the width and the sine of the angle, we get the total torque. Since length times width equals the area A, we can simplify the expression. We define the magnetic moment, mu, as the product of the current and the area. This allows us to express the torque more elegantly as the product of the magnetic moment, the field strength, and the sine of the angle. Torque is at its maximum when the loop's plane is parallel to the field, meaning the normal vector is perpendicular. Torque is 0 when the loop's normal is aligned perfectly with the magnetic field. If the loop consists of n turns of wire, the torque is simply multiplied by n. This principle is the fundamental basis for how electric motors convert electrical energy into mechanical rotation. In summary, a current loop in a magnetic field experiences a torque that depends on the current, the loop area, and its orientation. This concludes our lesson on magnetic torque. Generated by Vision Solve AI.